Hi, and welcome to the 4.07 Limiting Reactants teaching video. These are the Common Core standards that we're going to be applying to this lesson. The lesson objectives is in order to do limiting reactants, you must absolutely 100% have mastered lesson 4.06 stoichiometry. If you are not able to do the problems in 4.06, you will not be able to do 4.07 as we are adding on and building on to that stoichiometry. Please, if you have not mastered these previous lessons, 4.07 will not make any sense to you and you really need to go back and learn those lessons. Now we are under the impression that you are ready to go. 4.06 is no longer an issue. You know how to do that. So limiting reactants. What are limiting reactants? Basically, limiting reactants is just a whole bunch of stoichiometry problems together. You may end up having to do 2 stoichiometry problems or 3 stoichiometry problems in one. Limiting reactants are the longest math problem that you can do in chemistry, with the exception of AP chemistry, of course. Limiting reactants are basically if we are given exact amounts of both reactants. We have 2 starting amounts. Remember in the other recordings when I'm always talking about start with what you're given? Well, if you're given 2 amounts, you basically have 2 stoichiometry problems to do. And in doing that, we're going to be using and applying molar mass, which you've seen in several previous lessons, and molar ratio, which is from 4.06. This is a general outline of how to solve limiting reactant problems. This is not anything that you have to follow exactly. There are a couple of ways to do limiting reactant problems, and you may find that your teacher does it just a little bit different, and that's okay. And that's a nice thing about limiting reactant problems is that you can do it a couple of different ways. I recommend that you find a way to do it that gets the correct answer and is a correct way of doing the problem and stick with it. I'm going to teach you one way. This way tends to be just a tad bit longer than some of the other ways, but it makes a lot more sense logically. Okay, we're going to use the information that we've learned in previous lessons, and I'm going to do them in the same manner that I've been doing all the other recorded videos that I've done. So the first thing we need to make sure we have is a balanced equation. Sometimes you will be given a balanced equation, sometimes it will not be balanced. So you must make sure that the balanced equation. And then we're going to make a list of what we know and what we're solving for. So far, same thing as what we've seen before. The difference is that we might be given the exact amount of 2 or more reactants. If you are, you have a limiting reactant problem. So if you have a specific amount of 2 reactants, what you're going to do is you're going to set up 2 different stoichiometry problems. We're going to start each one with a reactant, and then we're going to convert, and this is super duper important, so make sure you highlight this. We're going to convert to the same unit of the same product. That is really, really important. We're going to use the conversion factors that we have already learned, molar mass, molar ratio, to do all the conversions that we need. And we have our new vocabulary. Whichever reactant produces the least amount of product is what we call the limiting reactant. That's the reactant that runs out. And the amount of product that it produces is what we call the theoretical yield. So you may have a problem where it says, what is the theoretical yield if blah blah blah. Okay, the theoretical yield means how much of your product can the limiting reactant form. Now in our problems we're going to have 2 reactants. We're going to have the limiting reactant, and then the other one is what we call the excess reactant. The excess reactant is the reactant that we have a lot of. Alright, so we're going to use these abbreviations LR and ER to represent limiting reactant and excess reactant. Kind of think of limiting reactant problems if you wanted a real life example, so to speak. If you're in the kitchen and you're going to make a very boring sandwich and you had a full loaf of bread Okay, let's say there's 20 pieces of bread in that loaf of bread, and you go to the fridge and you get your meat and you only have 3 pieces of meat. How many sandwiches theoretically are you going to be able to make? Well, assuming that we put 1 piece of meat on each sandwich, you can make 3 sandwiches, right? And then you're out of meat. So meat would be your limiting reactant. So your excess reactant would be your bread, because you have a lot of bread, you didn't use it all, so you have some bread left over. That's the same thing here in chemistry. Unfortunately, we don't have pieces of bread and pieces of meat. We have grams of oxygen and moles of water and grams of this and moles of that. And so our math is a little bit more complicated. But don't worry about it, because the math is the same stuff that you've been doing already. Okay, 99% of limiting reactant is actually 4.06 stoichiometry. Most of this lesson, 99% of this lesson, you've already learned from 4.06. We're just going to learn how to do 2 stoichiometry problems. So we can use the same flowchart as we used in 4.06. If we have mass of A, we can convert to moles of A. Then moles of A we can convert to moles of B, and then we can convert moles of B to mass of B. And in limiting reactant, we have the mass or the number of moles of 2 reactants, so we're basically going to do 2 stoichiometry problems. You already know how to do the stoichiometry problem, so now it's just a matter of doing it not once, but twice, maybe even 3 times, depending on what the question is asking for. Keep in mind that you're always going to the same final product, same product, if you're trying to figure out what is the limiting reactant. The best way to learn this material is to just do a couple of problems. We are going to be doing a lot of problems with this. You really need to take out a sheet of paper, calculator, pencil, periodic table, all of your notes, and you really need to do these problems on your own before watching me do them. Again, like I've said in other recordings, I can watch somebody play the piano for 500 hours. That doesn't mean I'm going to be able to sit down and play. I have to actually get there and try and struggle and start with chopsticks, or start somewhere. You have to start somewhere. You'll never learn stoichiometry and limiting reactants if you don't ever try it. You can't watch me do a bunch of problems and expect to know how to do it yourself. Okay, so please make sure that you're honestly trying these as much as you can. We are going to actually jump into our first problem. Go ahead, pause this recording. Try this, get as far as you can. Just remember, if you have the specific amount of each reactant, you're going to set up 2 stoichiometry problems, and you're going to start with each reactant, and you're going to convert to the same product. Use this flowchart here for each one. Get as far as you can, even if all you can do is just put your X's and your lines for the conversion factors. Get as far as you can, and then hit play when you're ready to resume. Welcome back. I'm going to go ahead and make a list of what I know. I know that I have 35.4 grams of this chemical. I know that I have 19.7 grams of this chemical. And it says how many moles of water. So here I have to solve for moles. So that's really important to remember what you're solving for. The question did not ask for grams, so I don't have to go all the way. And since I'm given a specific amount of both my reactants, I have a limiting reactant problem, which means I have to set up 2 stoichiometry problems. And each problem I'm going to start with a different reactant. So the first one, I'm going to start with my first reactant, which is 19.7 grams of SiO2. And then my second problem, I'm going to start with 35.4 grams of HF. Alright, now I'm going to use this flowchart. I'm given grams of A. I'm going to convert to moles of A. And then once I have moles of A, I'm going to convert to moles of B, and then I'm done. Okay, then I'm going to stop because moles of B is what I need. And my B is water because that's what I'm asked for. Alright, so when we start with what we're given, we put an X, we put a line. Whatever unit you start with, you put that unit on the bottom. So we have grams of SiO2. And this is going to be molar mass. We're going to divide by the molar mass. And remember that molar mass is the mass in grams of 1 mole of your substance. So we look up on the periodic table, we have silicon, we have 2 oxygens, we add all of that together and we get 60.09 approximately. My grams of SiO2 cancel. I have moles of silicon dioxide. That's not what I needed. I need to have moles of water, so I put another X, I put another line. Whatever unit is up top over here, I put that same unit down here. Now we're going to use the mole ratio. So we're going to have moles of silicon dioxide, and I'm going to put moles of the product that I'm looking for up top. Remember that my numbers here are the coefficients in the balanced equation. I see that they balanced it for me already. Silicon dioxide does not have a number out front, so that means it's a 1. Water has a value of 2 out front, so that's a 2. My moles of silicon dioxide cancel. I'm left with moles of water, which is actually what I was solving for. That's what the question asked for. So now I'm going to plug this into my calculator. Now remember the rules of fractions. You multiply everything on the top, and then you divide by everything on the bottom, and you should get an answer of 0.656 moles of water. What this means is that if all of my silicon dioxide reacts, I'm going to be able to make 0.656 moles of water. Remember my beginning problem. If I had 3 pieces of meat, so if I used all 3 pieces of meat, I could make 3 sandwiches. Do I have enough bread? Same thing here. If I use all of my silicon dioxide, this is how much water I can make. Well, do I have enough HF? Well, the only way to know is to see how much of my product will this make. So I start with 35.4 grams of HF. I do my conversion. Whatever unit I start with, that unit goes down here. Grams of HF. I'm going to look on the periodic table. I see that HF has a molar mass of approximately 20 grams per mole. Remember that molar mass is always of 1 mole. I have moles of HF. That's not what I need, so I'm going to keep doing my conversion. So I have to convert to moles of water. I know that water has a value of 2. When we look at our balanced equation, HF has a number 4. My moles of HF cancel. Moles of water is what I was looking for. That's what I have left in my equation that I did not cancel. Therefore, I'm done. I put an equal sign, and then I'm going to multiply everything on the top, and I'm going to divide by everything on the bottom. And when you do that, you should get approximately 0.885 moles of water. And now, we're not done. And please be careful when you do the worksheet for this lesson, because a lot of students will do the work and then they just submit their answer. And as a teacher looking at this, you have not answered the question yet. I don't know what your final answer is. How many moles of water can be produced? I see 2 answers. We don't assume anything, so please make sure that you circle or you type underneath what your final answer is if you wish to earn credit. And so limiting reactants, when we look at this, we have 2 different amounts of our product, don't we? So what the limiting reactant says is whichever reactant forms the least amount of product, that is how much water you're going to be able to form. So I am going to be able to form 0.656 moles of water. This is what I call my theoretical yield. Theoretical yield in moles. Theoretical yield is usually in grams, but we can just refer to it in moles here. Silicon dioxide is my limiting reactant, which means hydrofluoric acid or hydrogen fluoride is my excess reactant. Now, what this means is that my hydrofluoric acid could have made 0.885 moles of water. Since it could have made more, that means I'm going to have hydrofluoric acid left over. So when this reaction occurs, I'm going to use all of my silicon dioxide. I'm going to make 0.656 moles of water, and I'm going to make some SiF4, and I could do another stoichiometry problem and calculate how much of that I'm going to make too. And then I'm going to have some HF left over. So that in a nutshell is limiting reactant. There are tons of questions that we can ask you about it. Each problem's a little bit different, but keep in mind you're doing the same basic conversions. We need molar mass, we need molar ratio. You have to figure out where are you starting and where are you finishing. Do you need grams of your product or do you only need moles of your product? Are you starting from mass of your reactant or are you starting from moles of your reactant? If you're starting for moles or are asked for moles, it's a shorter problem. Notice how this problem was only 2 steps. Okay, and then depending on the question, you have to know the vocabulary. The limiting reactant determines how much product you can make. You may have to set up 2 problems like this if you were given exact amounts of 2 reactants. Whichever reactant forms the least amount of product, that is your limiting reactant. And that is how much of that product you will make. Okay, here's problem number 2. What I would like for you to do is go ahead and pause this recording, try this problem, get as far as you can, and then hit play to see how it works out. Welcome back. We see that I have 5.5 moles of aluminum. I'm reacting with 2.5 moles of HCl, and it's asking what is the theoretical yield of hydrogen. So when the problem just asks for theoretical yield, that means grams. Okay, just keep in mind, theoretical yield usually means grams, so we have to go to grams. So notice how we're starting with moles. We're actually starting with moles of A. We're going to convert to moles of B, and then from moles of B we're going to convert to mass of B because it's asking theoretical yield. I'm given a specific amount of both my reactants, therefore I have 2 stoichiometry problems to do. I have to start one with aluminum, and then the other one I'm going to start with HCl. And I'm going to set them up separately. So moles of aluminum, I'm going to put moles of aluminum down here. Notice if I start with moles of aluminum, I go right into the mole ratio. I don't need mass of aluminum. A lot of students try to convert to mass. Notice that when you have moles of A, you don't need molar mass. Don't use molar mass. You've already bypassed it. And then we look at our balanced equation. We see that it is balanced already. We have a 2 for aluminum. We have a 3 for hydrogen. So we're now at moles of B. Now we have to convert to mass of B. So whatever unit you have on top over there, that same unit goes down here. Converting moles to mass, we're going to multiply by the molar mass of that chemical, which for hydrogen is going to be approximately 2.016 per mole. Remember that molar mass is mass in grams of 1 mole of your substance. Do not look up here at the balanced equation. So many students are still doing that. The molar mass is about 1 mole. The only time you need the balanced equation is when you're converting moles to moles right here. Okay, so we have grams of hydrogen. That's what we needed. So we're going to go ahead and put our equal sign. We're going to multiply everything on the top. We're going to divide by everything on the bottom, and we get an answer of 16.632 grams of H2. I do not know if that's how much I'm going to be able to make because I don't know if I have enough HCl to do that. So now we're going to do another stoichiometry problem. We're going to start with 2.5 moles of HCl, and we're going to convert all the way to grams of hydrogen, just like we did before. So we have moles of HCl down there. We're going to use the mole ratio, and notice how some of this is very similar. HCl has a number 6, so our moles of HCl cancel. We have moles of hydrogen. We can convert moles of hydrogen to grams of hydrogen by using its molar mass. Notice how a lot of this problem is the same, isn't it? And hopefully that gets easier for you with time. The more you do on your own, the easier it will get. We're going to multiply everything on the top. We're going to divide by everything on the bottom, and we get an answer of 2.52 grams of hydrogen. Now when you're doing limiting reactants, remember you have 2 reactants with specific quantities. You set up your stoichiometry. You go to the same unit of the same product. Probably whatever product they're asking about would be the best one to go to. Now whichever reactant forms the least amount of product, that is your limiting reactant, and that is how much of your product you're going to be able to form. and that is your theoretical yield. When we look at our significant figures, we see that we should have 2.5 grams of H2. That is how much of our product we're going to be able to make. Problem number 3. Go ahead and pause this recording and try this on your own. Welcome back. On the left side, I see that we have 3 hydrogens. We have 1 phosphate group, one calcium, and we have 2 hydroxides. As products, we have 1 hydrogen, 1 hydroxide, 3 calciums, 2 phosphates. Again, balancing was from lesson 4.02. If you need additional help on balancing, please go back to 4.02 and watch that recorded video as I go a little bit slower and a little bit more in detail. Since we have already theoretically learned balancing, I am going through this rather quickly. I see my hydrogens are not balanced. In fact, nothing is balanced. I'm going to go ahead and just start with hydrogen. I have 3 on the left side, so I need to have 3 on the right side. Don't forget that that's going to change my hydroxide as well. So I now have 3 hydrogens. I now have 3 hydroxides. I need to have 3 calciums on the left side, so I'm going to put a 3 there. But don't forget that that's going to change the number of calcium and the number of hydroxide. So I'm going to have 3 calciums, and now I'm going to have 6 hydroxides. Because don't forget that that 2 here means that I have 2 hydroxides. So it's 2 of these times 3. So 2 times 3 is 6. My phosphates are not balanced. I'm going to go ahead and do that. I'm going to put a 2 here. Don't forget that that changes. So that means I have a total of 6 hydrogens. And then I have 1 phosphate group times 2. Therefore, I have a total of 2 phosphates. Notice everything's balanced except my hydrogen and hydroxide. So over here on the right side, I'm going to have to change. It's not going to be 3. I have to have a total of 6 hydrogens, a total of 6 hydroxides, so I'm going to put the value of 6 there. And then so that ends up being 6 hydrogens, 6 hydroxides. And now I am balanced. And I'm going to go ahead and clean up this board so it looks a little bit better. And there we go. It looks a little bit better now without all those lines. And now we have a balanced equation. Getting back to the problem, it says how many grams of calcium phosphate, so that's calcium phosphate, can be produced when 54.7 grams of phosphoric acid, so this is 54.7 grams, reacts with excess calcium hydroxide. That word is your best friend. And the reason why that word is your best friend is because it tells you that we have excess calcium hydroxide. Therefore, I know phosphoric acid is my limiting reactant. So now I only have 1 reactant that I know the exact amount. I have 1 stoichiometry problem to do. So I'm going to start with 54.7 grams of phosphoric acid, and I am going to convert to grams of calcium phosphate. Now use and follow your units. I have grams of phosphoric acid, therefore grams of phosphoric acid have to go on the bottom. Now the molar mass of phosphoric acid is 97.974 grams. That's using the periodic table. We have 3 hydrogens, 1 phosphorus, and 4 oxygens. Remember that molar mass is the mass in grams of 1 mole of your substance. I now have moles of phosphoric acid, but remember I have to get to calcium phosphate, so I'm not done. So whatever unit I have up top there, I have the same unit down here. I'm going to convert to my product, so calcium phosphate. I'm going to look at my balanced equation. I see that calcium phosphate has a 1, phosphoric acid has a 2, and now that I have moles, I'm going to convert to grams, and the molar mass of calcium phosphate is 310.174 calcium phosphate. These are long chemicals, aren't they? It's a whole lot of writing. Alright, so now we have our problem done. We have grams of calcium phosphate, so we're going to put an equal sign, and we are going to multiply everything on the top, and then we're going to divide by everything on the bottom. And the way that I plug it in my calculator is 54.7 times 1 times 1 times 310.174 equals divided by 97.974 equals divide by 2, and then you get an answer of 86.58. So with significant figures we need to round to 2, and I get 86.6 grams of calcium phosphate. Now this is the grams of calcium phosphate, so since this is what the limiting reactant forms, this is also what we call the theoretical yield of calcium phosphate. Okay, we can call it that. Phosphoric acid is the limiting reactant. Calcium hydroxide is the excess reactant. Water is just another product. I could, if I wanted to, set up another stoichiometry problem, start with my limiting reactant, and convert to grams of water and figure out how many grams of water I would form as well. I can do that, and you can do that too. Just this problem didn't ask for it, and I don't know about you, but I'm not going to do any extra work if I don't have to, right? And so even though we have the ability, we have developed those skills, we don't have to. We don't have to solve everything. We just do what the problem asked for. Let's match the word to its definition. Go ahead and pause this recording. First word is limiting reactant. The limiting reactant is the reactant that runs out. It forms the least amount of product. So these two go together. Limiting reactant is a reactant that runs out. It forms the least amount of product. The excess reactant is a reactant that is not used up. It's an excess. We have extra. Remember those shortcuts that we use. I do use these in my videos. Theoretical yield is the amount of product that can be produced when all of the limiting reactant is used. So again, the theoretical yield is how much your limiting reactant can form. So when you're doing these stoichiometry problems, you have to start with whatever your limiting reactant is. If you don't know what your limiting reactant is, that means you have to figure it out. If you're given a specific amount of both of your reactants, you have to do 2 stoichiometry problems and figure out which one is your limiting reactant. However much product that one makes is your theoretical yield. Once again, here's our general flow chart. Remember, you can do this as many times as needed for whatever problem you have. If you are going on to honors, you may have to do this 2, 3, 4 times for each problem, because in honors, it's going to ask about how much of the excess reactant do you use, how much of the excess reactant is remaining. So you may have 3 or 4 of these stoichiometry problems. If you need more practice, which you probably will, limiting reactant in stoichiometry is one of the hardest things that you can do in chemistry. It really requires you doing these problems and doing as many as you can. You can even go back, watch this recording again, do those problems again on your own, and then hit play to keep going and see the answers again. Do them over and over again. Check out the printable worksheet that is in the activity tab of the lesson. They have the answers worked out. Try those on your own. Don't look at the answers. The more practice you get, the better off you are. Thank you so much. It's been great working with you on stoichiometry and limiting reactants.